Bryce is here. Okay, so Bryce, we want to talk about Comet ZTF. So I'm going to stop this sharing and turn it over to you. You can share whatever you need.
Hey, how's it going? Thank you very much for having me at your meeting. So it sounds very fancy, Royal Astronomical Society of Canada. So it's the first time I've been to Royal anything having to do with astronomy. So I feel honored. So thank you very much. So I think most of you have probably heard of the Comet C 2022 E3. I guess I'll say a few things about myself to introduce myself. So I am a postdoctoral fellow researcher at Goddard Space Flight Center in Greenbelt, Maryland. And I'm studying principally small asteroids and the small bodies of the solar system, the asteroids and comets. Can you all hear me okay?
Yep.
So I got my start in astronomy, official start in astronomy, where I worked at the University of Hawaii, starting about 2012. And I worked on a survey called Pan-STARRS, which is a 1.8 meter telescope on the summit of Mount Haleakala on Maui. And started out as an all sky survey, but it progressively over time became more and more targeted towards finding asteroids and comets. And I had that job for a few years. And in that time, I personally found about 40 comets in the Pan-STARRS data and submitted those as observations, as discoveries to the Minor Planet Center, which became Comet Pan-STARRS discoveries. I'll talk a little bit about that in the talk, but after 2014, I took a break from hunting for asteroids and comets with ground-based surveys, and I went to the University of the French Riviera in Nice, France for my PhD studies, where I focused on dynamics of asteroid families in the main belt. It was more of a data analysis, more of a theoretical concept rather than observations, but I did do some observations on the side. And so when I finished the PhD, I moved to the University of Washington, where I was in principle going to be working on development of the pipeline for finding asteroids in the upcoming Rubin Observatory all sky survey. But I took a detour because I arrived at University of Washington right in 2017. And that was kind of the year of two really amazing events in astronomy. One was, is the kilonova, the discovery of the kilonova, and the multi-messenger follow-up of that event. But then there was also the discovery of the very first interstellar object, 1I Oumuamua. And so I was one of the first people to study this interstellar object, and with the Apache Point telescope, the 3.5 meter, which is also where the Sloan Digital Sky Survey is located. So I was one of the first individuals to study this interstellar object. And then after that, I moved to Caltech, where I worked on the Zwicky Transient Facility. And I was kind of going back to my roots, where I was hunting for asteroids and comets in the data taken by an all-sky survey, this being the Zwicky Transient Facility, which is a 1.2 meter telescope on Palomar Mountain that has a very large camera attached to it. It's about 25 by 25 centimeters of silicon chips that covers a very large swath of sky. So I'll talk about that. That's what led to the discovery of this comet. And I was at Caltech for 3 years when this happened. And now I'm at I've come full circle. Now I'm at Goddard. I moved here to Goddard last fall. So I'll share my screen here and get to the discussion of the comet. So I hope a lot of you have had an opportunity to see the comet. Um, I assume that y'all have made efforts to go and see it. So I have two. I think I've been watching the pictures of the comet come through on Twitter and Instagram and so on. And these are two of my very favorite images. So the one behind me is taken by an astronomer in Spain by the name of Javier Caldera. And I think it's just an amazing picture. I think I have a better picture of it in the presentation, but this was in late January when the Earth was passing through the orbital plane of the comet. And so you're seeing the comet, the distribution of the dust tail almost edge on. And so you see the full extent of the dust profile with a minimum of projection effects. And so I just thought this guy took an amazing photo, and you see the spectacular green color is just fantastic. And then there was this photo taken more recently. I believe this was this was last week when there was a conjunction of the two of Mars and the comet. They were within several degrees of each other. And I thought this was I think this was taken in Washington State. So they had amazingly clear weather serendipitously at this time of the year for the photographer to take this photo. And I think it's just a gorgeous photo. Mars is a little bit saturated, of course, but it's just an amazing contrast with the red and the green color in the sky. So if you were able to see this, you're a very lucky person. I wasn't able to see this, but I did see the comet. I did drive out to Joshua Tree on the 1st of February, right when it was at close to its closest approach to the Earth, and I got to see it with a very small telescope that I have. It's like just a little 4-inch refractor telescope, but with even just the unaided eye, I could see the comet. I could see the green color, and to me that makes it a fantastic thing. So I'll get on with the presentation. So I'm going to talk a little bit about the background of the solar system, and then I'll talk about the discovery and how it was made, and as well as some other work that I did with Zwicky Transient Facility. So in general, I'm just going to refer to the solar system, our planetary system. We know it's not special anymore. We see many exoplanet systems. We see many star systems that have debris disks. So the things of which make up comets and planets seem to be a lot more commonplace now in this in our current knowledge of the solar of the universe. But my concentration is focused of research in general is focused on the inhabitants of the solar system. And I think it's, I won't go into the reasons why I think it's a particular thing, but I think it's really cool that we can find things very close to us in our relative universe, our relative corner of the universe. This is necessary to talk about when we talk about the scales of comets, where they're coming from, but we typically think the immediate neighborhood of the solar system as being bounded by the planet Jupiter at 30 astronomical units. And then you have the Kuiper belt that is exterior to that, the Trans-Neptunian belt. But in reality, the full extent of our solar system goes out to tens of thousands of astronomical units away from the sun, where you really start to meld the boundary between interstellar space and the solar system itself. And we'll talk a little bit about why that is, but in reality, this is not to scale, of course, but the extent of our solar system is quite a bit bigger than what you would think it would be if it were just being bound by the ice giants and some of the more populated debris disks in the solar system. The main thing is that comets, they do come from a variety of different locations in the solar system. There is a distinction between what we call ecliptic comets, and then you have isotropic comets, and then you also have a new type of comet called the main belt comets. But these are more or less constrained. A lot of what we consider to be comets are more or less constrained inside the planetary region of the solar system. But we will talk about how they can act. There's actually reservoirs of comets that are very farly separated in space. So one of the reservoirs is the Kuiper Belt that is located at 30 to 50 astronomical units. It is a lot of it is dynamically heated up. That means it is not dynamically pristine. It has been affected by by gravitational encounters with mainly Neptune as well as the dynamical interactions with the gas giants and ice giants as they migrated throughout the solar system. There is a component of the Kuiper Belt that is primordial, that is dynamically primordial, but the majority of the Kuiper Belt is actually very dynamically disturbed, let's say. And this is what actually allows us to get comets from it, ecliptic comets, which we see as the periodic comets. The majority of the periodic comets, the Jupiter family comets, come from the Kuiper Belt. And then you have this the structure called the Oort cloud. So the Kuiper Belt is more or less confined to the ecliptic plane within some tens of degrees of inclination for some of the more dynamically heated members. But unlike that, the Oort cloud is a more isotropic entity, more isotropic structure, and that is much more distant, that can extend out to the very boundaries of the solar system to tens of thousands astronomical units away, and be oriented sort of anisotropically all over the isotropically all over surrounding the sun. So the way that the comets are transferred from this cloud is they are on circular orbits for very, very distantly, but then there might be some kind of disturbance where they encounter a star at these large distances, a passing star. You have these really high proper motion star like Baynard star is one. Baynard star isn't come as close to the solar system as a lot of stars that we would expect to have passed by, which would disturb comets and send them on to trajectories that encounter the planetary region. But there are stars like that. There can be brown dwarfs as well, some kind of massive body out there that can disturb the orbit, the relatively circular orbits of these isotropic comets, and send them on highly eccentric orbits into the inner solar system. You can also have galactic tides, which shape the Oort cloud. But the main thing to know is that the Oort cloud as a structure is something that is not primordial. It did not form with the formation of the solar system. It came afterwards. And that you had to have had the Oort cloud form when the sun cleared its original birth cluster. Otherwise, you would have the stars and its immediate birth cluster would have dispersed the Oort cloud. But the fact that we do have an Oort cloud is that we have these comets that come on trajectories into the inner solar system suggests that it formed later. And this is they were basically the planetesimals that it created in the protoplanetary disk, and then subsequently to the sun leaving its birth cluster, they were ejected into the Oort cloud by gravitational encounters with the gas giants. So as I mentioned before, so you have these two reservoirs, the Oort cloud and the Kuiper Belt, where you have these two different kinds of comets. For the Kuiper Belt, you have the ecliptic comets. In the Oort cloud, you have the isotropic comets, like the very long period comets, like the kind of which ZTF is. You also have another kind of comet, it's called the main belt comets. And so these are comets that actually originate from inside the asteroid belt. They're not actually captured there. They're not something that dynamically diffused and found its way into the asteroid belt. They actually originated, they actually formed in the protoplanetary disks into the confines of the asteroid belt. And these are a very different animal though. But I'll mention some pictures here. When I was at the University of Hawaii, I found two of these at the time when there was only about a dozen of these known. One was called Comet 311P Pan-STARRS. So the top picture of it is the image as it appeared in the 45-second R-band image taken by the 1.8 meter Pan-STARRS telescope. That was the discovery that led to the discovery which I found in the data. In this bottom panel right here is a Hubble Space Telescope image taken of it following its discovery by Dave Jewett. And it's pretty remarkable. The comet has 6 or 7 tails, multiple epochs of activity, which suggests it's a very different animal from what most comets are found. And then I found another one called P 2013 R3. And this is a co-discovery with Catalina, the Sky Survey. But this is an asteroid that actually became disrupted, where it split apart into multiple pieces. And so this is a discovery image from Pan-STARRS, and you can see the multiple pieces here, just barely. But there's a follow-up image taken with Hubble that shows the multiple pieces much more cleanly. But I just wanted to show this is the comets are not just from the Oort cloud and the Kuiper belt. There's also comets, cometary-like objects in the main belt. And I think the Chinese Space Agency, they want to send a spacecraft mission to this 311P Pan-STARRS. And so it's pretty neat that, if you get to discover something that a spacecraft gets to go see. So we see the comets, we see the dust tail, we see the coma and everything. But what do comets actually look like, and why do they look like this? So this is an image of 67P. It's a periodic comet, short period comets, Jupiter family comet that was visited by the Rosetta spacecraft. And so there's discussion that these comets, that they have this kind of rubber ducky looking shape. You have this bilobal shape, and the discussion is that this is a collision between two different bodies in the primordial planetesimal belt, and they got kind of as a slow collision and kind of an elastic collision that resulted in these two bodies kind of sticking together. But a lot of comets, this is just one example, but a lot of comets kind of have this kind of bilobal shape. And so now we're looking a little bit further away. This is from Comet Ison. Does anyone remember Comet Ison? This was the naked eye comet, or near naked eye comet, that was found in I believe 2012. And I remember this because Pan-STARRS, it was found by 2 Russian astronomers in Russia, I believe, who built their own telescope. And they discovered this comet, but if they hadn't found it, we would have found out like a week later or something. So we were a little bit disappointed when they found Comet Ison before we did. But this was a comet that was, I think, visible from the southern hemisphere. And I tried to go out and look at it, but I got clouded out. And then you have Comet Hyakutake. This is another really good one. I think in 1996. I didn't get to see it. I don't remember it. But it was one of the greatest comets in the last 30 years. And the main thing is that most comets are more, the nucleus is going to be a few kilometers in size, but the tails are huge. They can be hundreds of thousands of kilometers, like an astronomical unit. And so it's a real structure in space, something that is just on the Titanic proportions, as you would on the scale, on a considerable amount of scale length within the confines of the solar system. This is Comet Hale-Bopp. I remember I did get to see this one when I was a kid, and this one was really nice. You had the nice ion tail, you had the dust tail, and I think this was also very scientifically exciting. There was a lot of this object was followed up by a lot of observers who studied its gas production contents over a long period of time. But we see this with E3. You see the kind of bifurcation of the tails, and they're kind of one and the same, but also kind of not. So you have these two separate tails because the physics that is affecting these are very different. So for the dust tail, you have the action between the radiation pressure that results from the sun's light that is acting on, that's a non-negligible momentum from the individual photons from the sun's light that is acting on the dust particles, which is providing a non-gravitational acceleration and the vector direction that is opposite to the sun. However, the dust particles also have considerable amounts of mass, and so they have inertia, and so they follow a combined vector between the comet's orbit and the acceleration, non-gravitational acceleration that results from the solar radiation pressure, which is in the radial direction from the sun. So you have this dust tail that is kind of in between the anti-solar direction and the comet's orbit. Now the ion tail is a bit different. The ion tail consists of charged particles that interacts with the solar wind. The solar wind moves at 600 kilometers a second. It's a non-negligible fraction of the speed of light. And so this solar wind is moving very, very quickly. These charged ion particles, which in themselves and on an individual basis are a lot lighter compared to the individual dust particles. Dust particles and comets tend to be on micron scale. That's why we can see them. But the gas ions operate on a different type of physics. What you see as the ion tail are actually gas molecules, and those move under the influence of the solar wind a lot more quickly and compared to the dust tail. And so that's why when you see a comet, you see two separate tails, because the anti-solar direction for the ion tail is a much more apparent compared to the total sum of the vectors of the forces affecting the dust tail. And so sometimes they can be coincident, but most of the time that you are going to see a comet, if it's not edge on, if you're not inside the orbital plane of the comet's orbit, the Earth is not inside the orbital plane of the comet's orbit, like you're seeing in Javier Caldera's really nice picture they took on January 23rd. You will see the two comets tail separate. I also should note that there's a better picture of it coming up, but when you're looking at the comet at an angle, at a considerable planetary angle, you're seeing more of the distribution in the different dust sizes, because not all the dust in the comets is the same size. They actually spread out and sort according to their individual sizes. So this was a really nice picture, movie taken by Nick James. He is on our minor planet working group body, and he saw this really nice kind of evolution in the ion tail, and he indicated this had to do with a change in the solar wind. And so you can see this was in mid-January. You can see that the tail was a lot thicker at one point, but then something in the solar wind changed, and now the tail became a lot more collimated. I don't understand the physics of the ion tail so very well, but I believe that this has to do with the change in the velocity of the solar wind. So this is Javier Caldera's amazing picture he took on January 23rd. And so I just want to note that there's a couple of different features here. So the solar direction, we're basically looking at the comet kind of edge on, or let's say down the barrel, let's say, and the sun's direction is kind of behind our back. And so there's this discussion of an anti-tail, and this is not really like a tail that is going in the direction of the sun. Sometimes you can have comet dust that is ejected in the radial direction towards the sun, and then it gets blown back out into the anti-solar direction. But for a structure that is this large, that this is tens of thousands of kilometers in size, that this is not actually going in the direction of the sun. It appears to be going in the direction of the sun, but what we're actually seeing is the more full extent of the three-dimensional shape of the comet's tail, and the comet's dust structure. So you can see the ion tail here. The ion tail is very distinct, and because it's a lot more collimated and a slightly different color than the green kind of hue and the rest of the dust, the more white color of the dust. but the ion tail is more like a very fine smoky white in this image. But you will see, because we're staring at the comet basically edge on, we're seeing the full extent and the perpendicular direction that the dust is ejected perpendicularly to the orbital plane. So you can see the dust particles that are overlapping on each other in the transverse direction and the radial direction, of course, but we can actually see with the minimum projection effect the full extent of the comet in the perpendicular direction to its orbit. And so this is nice because it gives you a direct constraint on the ejection velocity of the dust. So there's some really nice examples. So people talk about the green comet, but comets, the green color is very common for a lot of comets because this green color results from the emission of photons after being absorbed by cyanogen gas and diatomic carbon, which are fairly common daughter molecules for comets that are in the interplanetary region. So we do not really know what the parent molecule of diatomic carbon, but what we do know is that we know somewhat how the physics affects this mystery parent molecule. It's probably some kind of hydrogen carbon molecule that it gets released as a chemical with the volatilization or the sublimation of ices and other cometary volatiles that becomes photo-dissociated due to the sun's light in space, and this can occur over a time scale of days. So it's a steady state. So the parent molecules of cyanogen gas and diatomic carbon are in steady state being released by the comet, but then within less than 24 hours, they're being photo-dissociated into diatomic carbon and cyanogen gas, which in and of itself gives this comet, when it is energized by the sun's light, it gives this kind of green glow. And so you might think, okay, maybe the green comet is not so special after all. But I remember I didn't get to see Comet Ison in person, but for example, Hale-Bopp and Hyakutake, you could not see the green color with your naked eye. With this with the E3, when I went out to the desert, I definitely saw a green glow to the comet, and it was just absolutely amazing. So how was the green comet found? C 2022 E3. So I'm going to talk a little bit about the technical details with how the comet was found. And so this is an aerial view of Palomar Observatory. So this right here is the Palomar 200-inch. It is humongous. It is a ginormous building. Modern day telescopes for their size are in a much smaller enclosure, but you can see the cars right here, and that kind of gives you an idea of what the scale is. It's a 5-meter telescope, but this dome is basically the size of Keck. Keck is a 10-meter telescope, and the reason is that it's built with old technology and different. They didn't have computers that could properly operate Altez mounts, so they had to make everything equatorial, and that makes the scale much larger. But in any case, the work was mostly done here using the Palomar 48-inch telescope at Palomar Mountain. So here is the enclosure. It's kind of similar to in appearance, like a little brother of the Palomar 200-inch. It has the kind of Art Deco design. It was built in the 50s. The Palomar 200-inch was built in the 30s and 40s. So I think it's some kind of architecture design that was typical of the time. But the reason why it's the Palomar 48-inch, it's the official sponsor is Samuel Ocean, who is actually also the same guy who sponsored the telescope at Griffith Observatory. It's kind of funny, but he sponsored this telescope. But the instrument that is mounted on it is called the Zwicky Transient Facility. And so what the Zwicky Transient Facility, it's a camera that is on the Palomar 48-inch that has like a 14-inch by 14-inch, which I think that's going to be like 30 centimeters or so if I do my metric conversion correctly. It's a very huge piece of silicon. I've seen it in person, and it's a very impressive piece of silicon. And so I've seen Pan-STARRS one in person, and that one was pretty sizable. I remember that was like the size of a fairly large dinner plate. But this thing right here is like, the size of a tray or something. Like bed and breakfast trays. It's this huge piece of equipment. And it's mounted in so the Palomar 40-inch is a Schmidt telescope. So it has a different kind of optical design, but the camera is basically mounted backwards. And it has filters that are so huge that it has to have a robot arm that gets a filter and holds it kind of like a ping pong ball paddle and puts it on the top of on top of the camera. So it makes it changing filters somewhat of a time-consuming process, but it's an important process, and it is something that is incorporated into the design and works fairly well. But the main thing here is that the Zwicky Transient Facility has a 47 square degree field of view. So it's about 7 by 7 degrees on a side, which is huge. Imagine the full moon and multiply that by a factor of more than 10. And that is the size of one image of the Zwicky Transient Facility. Now, the pixel scale is not the greatest in the world. It's only about 1 arc second. But the Palomar site doesn't have the best seeing in the world. So to be honest, a lot of the time it still ends up being Nyquist sampled, even with such a large pixel scale. But in general, the Zwicky Transient Facility takes 30-second exposures, typical seeing, typical observing conditions during dark and gray time, plus or minus 5 or 6 days of the full moon. We get to about a beam magnitude of 20 in a single 30-second exposure. Now, here is, if you're curious what the telescope looks like, this is me standing by the telescope. That blue box right there is a Zwicky Transient Facility that has the electronics in it, and as well as the filter exchange. The actual camera is inside the bore of the telescope, inside the actual body of the telescope. And so to change the filter, the telescope has to point to zenith, and then a robot arm comes out here and puts a filter in and covers it on the camera, and then brings it back and replaces it itself. Another thing you keep in mind is that because of the size of the camera, the size of the image plane, you have to have a shutter at the end of the telescope, not inside the telescope. It's not just a piece of camera that is covered up by the shutter. It has the entire aperture at the end has to be completely shuttered, and it's pretty big. So imagine a 1.2 meter size shutter closing and opening every 40 seconds or so. So it has to be very mechanically reliable and very quick. And I've been in the building when it was operating, and it sounds like a guillotine. It's a very loud noise when that shutter opens and closes. And I'm pretty sure you might, lose a limb if you were to put your hand inside when it was closing. So it's technical. It's a technical requirement for how the survey is designed to scan the night sky very quickly, to have to operate with these kinds of conditions with a robot arm, having to change the filter as quickly as possible over such a large image plane, and then having the filter open and close over a very large aperture in order to completely obfuscate the very large detector image plane that the large detector is inhabiting. But what this gives you the ability of is that it can cover the entire night sky to V of around 20.5 during dark gray time every few days.
What about vibration, Bryce?
So it's actually really good. These telescopes are all really old. They're this Zwicky Transient Facility, the Palomar 40-inch was built in like the 50s. And I don't know where they get their money to keep things operating so well. and looking so cleanly. But the telescope runs very, very well. It's settled. So the time between exposures, subsequent exposures, is so it's about 30 seconds for the exposure, and then it's about 7 seconds to read out, and then it moves to the next field within 40 seconds. So every 40 seconds, it has slewed and taken a new image. So the settle time is very, 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 very quick. Even though the shutter opens and closes, it's not a it does not cause an additional settling at the settling budget. The telescope moves very, very quickly. It's all roboticized, and it's fairly impressive piece of machinery that, despite it's almost it's approaching 70 years old, over 70 years old. It runs extremely well. I think it also helps that it's a equatorial mounted telescope, so that might help as well. So this just kind of give you an idea of comparison with other facilities. So there are other all sky surveys. I mentioned Pan-STARRS before. I used to work for Pan-STARRS. It's a 1.8 meter on Mount Haleakala. You have the Catalina Sky Survey, the 1.5 meter Schmidt telescope that is on Mount Bigelow, and you have the 0.7 meter. No, sorry, 0.7 meter is the Schmidt, and the 1.5 meter, I believe, that is a I think that is going to be an RC design, Ritchie-Chrétien telescope. But those are in southern Arizona, and then you have the Atlas telescope, which is an amazing project. It's expanding. So they have 2 sites in the Hawaiian Islands. You have one on Mount Haleakala, you have one on Mauna Loa, but that one is being moved because the volcano, I think, started becoming too active. And it didn't get destroyed, but I think they had to shut down for a little while, and I think they're probably going to have to move it. But they just opened up 2 new sites. One is in South Africa, and Atlas South, and one is in Cerro Pachon in Chile, near where Gemini Telescope South is located, and is also where the Rubin Observatory is being assembled. And then there is also the Neowise Telescope, which is in polar orbit, looking at quadrature. It's an NEO survey. It was very prolific, continues to provide excellent data. But our domain on the ground, the Catalina Sky Survey is primarily used to find NEOs. Pan-STARRS is now primarily used to find NEOs. Atlas as well. It moonlights as a supernova survey as well. But ZTF is not primarily designed to find asteroids and comets. It's kind of a side job for it. It is primarily designed for astrophysics. It is primarily designed to find supernova, as well as to study the other very short-term transients. So when we talk about ZTF, I was not just only operating the asteroid finding aspect of the project. I was also involved in follow-up, because it's not just enough to find an asteroid in the data. You actually need to follow it up, or else it will get lost and you won't make your discovery. So there's 2 different kinds of follow-up. So you have discovery with the Palomar 48-inch, but then you might do imaging follow-up with the Palomar 60-inch. It's a telescope that is primarily an integral field unit spectrograph designed to do quick follow-up of supernova, but it also has a camera mode which we use to follow up asteroids and comets in order to provide astrometric follow-up in order to refine their orbit. This is a very important aspect of comet discovery and asteroid discovery. Otherwise, you can just detect something, but you will not actually get the discovery credit for it unless its orbit is confirmed well enough to where it can be recovered in the future. And then you have the kind of follow-up where you are doing detailed scientific classification. And so for this, we use the Palomar 200-inch telescope. It has it's primarily used for a spectrograph, but I like to use the imager a lot. I might show you a picture. I took a picture of the comet with the Palomar 200-inch, and you can use that fairly well to image comets and study comets. We also use Keck. Keck is used a lot by the supernova people to follow up really faint astronomical transients. Sometimes I ask them a favor and they might observe a comet or an asteroid for me. Spitzer is no longer with us, but we are looking for other ways to do the kind of follow-up with the near infrared with spaceborne telescopes. Sometimes we use this global network of telescopes called the Growth Network, which is located around the world. There's several sites in the West Coast. We have sites in India, as well as in Taiwan, and going that way around the globe. We also have a site in the Canary Islands, which is the Liverpool telescope. And this kind of network gives us almost 24-hour coverage of the night sky in which we can do follow-up. Sometimes we also do more space-based follow-up. I have not done any space-based follow-up with a James Webb Space Telescope of ZTF targets, but I have done a few follow-up with the Hubble Space Telescope in order to provide high-resolution imaging of cometary objects. So this is the kind of rough breakdown of the different categories in which we find moving objects, asteroids and comets with the Zwicky Transient Facility. So to date, we have found about 200 near-Earth objects, which are found with a couple of different means. One is called Z-mode, it's like an automated blink comparator. You are looking for the detection of moving sources from one image to the next. Then we have, and I'll go into a little bit more detail about how these individual things work, but this is just kind of a rough breakdown. And then we have something called Z-streak, which is detection of fast moving objects. That these are asteroids that are moving more than a few degrees per day, asteroids that are moving so quickly that within a 30-second exposure of the Zwicky Transient Facility, it trails considerably more than a few arc seconds, enough that you would detect it as a elongated detection instead of a point source-like detection at the seeing and sampling that we have with the Palomar site and Zwicky Transient Facility instrument. This algorithm is like a trail recognition kind of thing. It operates on an individual image basis. It does not need multiple images together. It actually uses machine learning to artificial intelligence to look at a detection and recognize it as an elongated detection or not. And then we have something that I co-developed with a computer scientist by the name of Dmitry Duev. That is designed purposely for the identification of comets and ZTF image data. It is kind of like the Z-streak in the sense that it can look at individual images and find comets on it. This is one example right here. I believe this comet right here was one of the it's not a discovery, it's a known comet. I want to say that it is going to be one of the really common, one of the really well-known 46P, I believe. So the concern that I had when I started at Caltech was that because ZTF was a astrophysics survey, it was not optimized for finding comets because ZTF basically excludes any kind of an extended detection. We have a solution for that for the streaks, but for comets, which are by nature extended objects, we do not have a solution for. So what would happen is that the pipeline would automatically reject all cometary detections, all cometary objects. And it does this for false positives because of the very large detector plane of ZTF. It is very difficult to mitigate stray light within the optical design of the telescope. So because you have such a large image plane, you are going to have stray light, you are going to have artifacts which will have an extended appearance on the detector plane. And in order to reduce the number of false positives in your data stream, there was a decision to automatically reject all extended sources that were detected in the automated data analysis extraction pipeline for the Zwicky Transit Facility. So this concerned me greatly because ZTF had not found any comets, or it would be very difficult to find a comet with ZTF. Before I started at Caltech, there was someone who found 1 or 2 comets, but it was like a special, very specialized thing. It was not the usual operations. So I worked with Dmitry Duev, who is a computer scientist and astronomer, who is an expert in artificial intelligence, where we trained a neural network to identify comets on an individual image basis in the ZTF data in order to circumvent this issue with extended objects being eliminated from the data pipeline. So this is kind of what it looks like. Dmitry Duev built this very sophisticated website, basically, that had the output of tails of what we call the tails pipeline. And in my job, I would look at this every night. We might have between 500 and 600 candidates and in a night's worth of data. Now, we wouldn't run the tails pipeline on all the data. In reality, we only ran the tails pipeline on about 10-15% of the data. So if we had let the pipeline run on all the ZTF data, the number of candidates would easily go up by a factor of 5 or 10. And that would be, I would do it, but we were more limited by the fact that this was running on Google Cloud Surface and we did not have enough credits. This was kind of a prototype at this point. And then Dmitry Duev went to go do some other things, made a career change, and we did not get to implement the full the full running of tails on all the ZTF data. But in the time that we got tails implemented, which was at the end of 2020, until when I went to Goddard Space Flight Center, we discovered about 10 comets with a combination of the tails pipeline and the ZTF data stream. One of which was the C2022 E3 green comet. So I'll talk a little bit. So not only do you have the data pipeline, you also have the survey cadence. So I mentioned that the ZTF data that we ran, the tails pipeline, was only about 10% of the total ZTF data. And that 10% that we chose to run the pipeline on was something called the Twilight Survey. So the Twilight Survey is what we call a sun-centric survey, a survey that is designed to find asteroids, and now with tails, we can find comets on very small solar elongations. So this is a sky distribution map of a very short subset of the Twilight Survey field pointings that were taken at the end of 2019 and early 2020, but I overplotted some of the discoveries that were made in the Twilight Survey data. So the green comet was found in the Twilight Survey data on the morning side of the Twilight Survey. So the Twilight Survey would run for about 30 minutes during evening twilight when the sun was at minus 18 degrees below the horizon. And the ZTF survey could point as low as 20 degrees from the 20 degrees elevation. So we could look to within 40 degrees of the sun, but in reality, we would look between 40 and 50, 55 or so degrees from the sun. So in the evening, we would do this for about 20 to 30 minutes. And in the right after at 18 degrees, 12 to 18 degrees twilight. And in the morning, we would do this at 18 to 12 degrees twilight right before the sun rose. And so the green comet was found in the morning direction at an ecliptic latitude of about 25 degrees. Now, the thing to keep in mind is that ZTF is located at 30 degrees latitude. So the ecliptic does run through 20 degrees latitude. However, it makes a kind of a diagonal. It's at a diagonal to the equatorial plane. And so as a result, we cannot always look exactly at 0 degrees or as low as latitude as we can. So that is why when you're looking at this plot, there is sort of a center of mass for both the evening and the morning twilight survey that is significantly above the ecliptic latitude that is of 0. And so where we found C2022 E3 was at a positive latitude of 25 degrees, which is where we could point the majority of our pointings for the twilight survey due to the plus 30 degree latitude of the Zwicky Transient Facility, the Palomar Observatory location. So this is a plot that shows the sun-centric distance which the twilight survey operates on. So this is a cumulative distribution. So about half of the fields are within 46 degrees of the sun. Now, where we found C2022 E3 was about 39 degrees from the sun. So it was actually, at the time that we saw it on March 2nd, 2022, it was actually on the morning side within 40 degrees of the sun. The majority of the fields of the twilight survey are 80% are on sun-centric distances of more than 40 degrees. So we got somewhat lucky that that small 20% or so portion that was within the range of where the C2022 E3 comet was located covered that part of the sky in the morning for us to make the discovery. Now, this is an example of Z mode. These aren't the discovery images of the comet because I do not have those anymore, but this is an example of what it looks like to employ the Z mode method of which you are finding moving objects. It is like an automated version of blink comparator work that people like Clyde Tombaugh use to find moving objects. The manual method was actually employed quite effectively at Palomar through the 80s. And it was actually quite a few interesting discoveries were made at Palomar using this method. But now we've automated it using computers using the blink comparator method. And so this is a stack, 150-second stack of the comet image. So the comet was detected in 5 30-second R-band exposures on the morning of March 2nd of 2022. Sorry for the typo there. But this is a composite stack. Now, it is not immediately obvious, even with 150-second exposure, that this object had a cometary nature. It does not have a tail. And the image quality at the Palomar site is about 2 arc seconds, 2.5 arc seconds, especially when pointing at these high air mass fields. So at the time when I saw this comet in the images, it did not immediately leap out to me that this was a cometary object. However, on our machine learning pipeline, Tails, it reported that these detections had a 60% probability of being a comet or more likely to be comet compared to average. However, at the time that I saw these images, I did not want to make based on the evidence after stacking them, it was not conclusive enough to say that this was yet a comet. So the comet was submitted as an asteroid, particularly as a near Earth asteroid. Now, there was an indication that this object was a comet because at the time it was discovered, due to its large ecliptic latitude, there was enough information that suggested that it had a very high inclination of more than 90 degrees. Now, I mentioned before that comets can come from 2 different reservoirs. You have comets which come from the Oort cloud, and you have comets which come from the Kuiper belt. You also have main belt asteroids and the asteroids from the near-Earth asteroid population. Typically, when you detect asteroids which are from the main belt, and you detect comets which are from the Kuiper belt, they're typically within 10 to 15 degrees of the ecliptic, and they will have inclinations of less than 20 to 30 degrees. However, isotropic comets, the Oort cloud comets, can have inclinations that are retrograde. This object on its initial orbit had an eccentricity of about 1 and an inclination of 98 degrees. So that was a suggestion, and a perihelion of 1.1 degree, of 1.1 astronomical unit, which is with its high inclination, with its high eccentricity of almost 1, implied that it had a semi-major axis of tens of thousands of astronomical units. These factors combined strongly suggested that this object could be of cometary origin. So when that happened, the cometary follow-up community considered this to be an object of interest and followed it up closely. Now, we followed it up closely as well. So on the left-hand panel here is the Comet ZTF that we followed it up about a few days later after the initial discovery observations made with the Zwicky Transient Facility. So this was a 300-second exposure with the Palomar 60-inch telescope. And yes, you can start to see that it has somewhat of a tail. So the sun direction is plotted in red. I'm pointing in the direction of the sun. And you can see in the anti-solar direction, you can see that there is somewhat of an extended morphology. Now, the background stars are trailed due to the fact that we are targeting a moving object. We're tracking along the motion of the object, which we now know due to its preliminary orbit. So the extendedness of the comet itself is due to its extended light scattering cross section, and not an artifact of the tracking. So this is when we knew, okay, this is going to be an interesting object. We saw that it was going to approach the Earth within 0.29 astronomical units in early February of 2023, and may reach a visual magnitude of 5. So now I'm going to talk a little bit about some other Zwicky Transient Facility work. So I mentioned before that we had the 2 different modes. You had Z mode, which finds the blink comparator method of finding asteroids, and you have Z streak, which finds the elongated asteroids. So this gives the ETF the capability of finding not only slow-moving objects, quote unquote slow-moving objects like the comets and some of the asteroids that it sees in the Twilight Survey, but also objects that are moving very, very quickly. So on the x-axis of this plot, I have the rate of motion in arc seconds per minute. And on the y-axis, I have the absolute magnitude. So the absolute magnitude is kind of a proxy for size. Between an absolute magnitude of 15 and 30, you have the size scale of thousands of meters to about 1 meter beach ball size. And you can see here there is this gap in between Z mode and Z streak, this kind of bifurcation between 2.5 arc seconds a minute and 25 arc seconds per minute. And that is due to the fact that you have the pipeline that is going to reject things that are marginally extended, and that we have the Z streak pipeline that is picking up this, that is activating on those which are significantly extended, just enough to become extended by more than a few pixels in a 30-second exposure. Now, the thing to note is that the Z streak objects are a lot fainter in absolute magnitude. And this is because objects which are moving fast enough to become streaked on an individual 30-second exposure are going to be closer to the Earth. And by consequence, you can see things which are fainter when they are closer to the Earth. So this is the sky detection pipe distribution on an ecliptic coordinates. So I wanted to highlight the fact that this is an astrophysics experiment. It is not a planetary science asteroid hunting experiment. if this was an asteroid hunting experiment, you would see the majority of the fields, which are the color-coded background, hugging the ecliptic like you would see for the Catalina Sky Survey. But in this case, the optimal strategy of the survey is to cover as much sky at as much low air mass as possible for maximum throughput. And due to the 20 degrees latitude of the survey is going to be following the ecliptic. It's going to be more biased towards following the equatorial the equatorial plane as opposed to the ecliptic plane. But it is also interesting to note that the Z streak and Z mode discoveries are somewhat evenly distributed across the sky, correcting for the bias and the amount of which survey is covering that part of the sky. And so this is my favorite way to look at surveys, is the opposite centric detection mode. If you observed asteroids and comets before, you know that they are going to be at their very brightest at opposition. So as a consequence, we make most of our discoveries at opposition. But then you see these little moon-shaped things here to the side that are at opposition centric ecliptic longitude, about 150 and minus 50, and these are the twilight surveys themselves. This is where the parts of sky in which you would find the comets like C2022 E3. So this is the website that we use to bet. So we have 3 different websites. So we have a website for tails, which is for finding the comets, and we have a website for Z streak itself. And I employ when I was working on this, I employed volunteers, a lot of really good students from all around the world, including Indian Institute of Technology in Mumbai and National Central University in Taipei, Taiwan. And I also worked with some students in France and in England as well. So the idea was to have people at different time zones looking at the data that were coming in, and to alert if there were asteroids that were close approach with the Earth. As you know, there was an asteroid that impacted Normandy, France, 1 meter just about a week ago. And then some months ago, we had the really nice detection of an asteroid by Catalina Sky Survey that hit London, the London area. So I hope that you got to see that, or maybe got to go collect some meteorites. I know there were some people who collected meteorites of this most recent Normandy impact, but that is what we're trying. That is the goal here, is to have a real-time 24/7 monitoring of the data with follow-up while we are taking data in order to find these close approaching asteroids. So we found quite a few. We found some close approaching ones. One is called 2020 QG, 2021 CZ3, 2021 JU6, and 2021 SP, and 2021 XL. And these are what I call close approaching because they approach within the range in which we have the satellites, geocentric satellites, and some of the more distant satellites. And one was the second place in terms of close approach, but not hitting the Earth, and that was 2020 QG. But this shows the MOID and color code, that is the minimum orbit intersection distance between the asteroid's orbit and the Earth's orbit as a function of absolute magnitude on the x-axis, which is a proxy for size, and the time of the discovery. So this is why we have to have the kind of the 24-hour monitoring thing, is that for these really close approaching, really small, tiny guys, we typically don't have more than a day or two of warning. And a lot of them we see after the fact, after they've already had the close approach. So this one was the 2020 QG object. We saw it a few hours after it approached within 30,000 kilometers over the Indian Ocean. And this was the second place closest approaching asteroid to not hit the Earth. First place was one that's found by Atlas. So we held the record for first place for about 2 months. And then Atlas found one that came within like 400 kilometers. So beat us by an order of magnitude. But these are, I just want to note here when I talk about I put the size here, absolute magnitude. These are really, really small guys. They're on the meter scale. So, no need to worry if one of these hits us. It would be pretty exciting. You'd want to go and see it and try to collect some meteorites afterwards. So we had another one, 2021 JU6, that we found before the close approach. But it came pretty close, but not super close. And then we had one called 2021 SP that came within some of the range of the satellites. And at the time it was discovered, it triggered the alerts and said that it was going to impact somewhere over East Asia. So that was pretty exciting. It's the one that hit last week. It triggered the alert, and I think it had like a 20% chance impact when it triggered the alert, and then that 20% chance rose to 100% chance. But for the majority of these cases, that chance of impacting the Earth is ruled out fairly quickly. So another one of the few, I'm wrapping up here. One of the things that interesting discoveries that we made with ZTF, in addition to that green comet and some of these close approaching things, were the discovery of inner Earth and the very first inner Venus asteroid. So these are called Atiras. Atiras is the name given to the class of objects which are just inside the orbit of the Earth. But in 2020, I found the very first asteroid, which was located entirely within the orbit of Venus, called 2020 AB2. And that's this black orbit right here. Sorry, it's kind of hard to see because I have some of the other discoveries on there. But this now has the name Aeolochaxnim, which is the San Luiseno in San Luiseno language, which means the Venus daughter. So the name of the class of these asteroids that are located inside the orbit of Venus are now going to be named after the prototype Aeolochaxnim. So I mentioned a little bit about follow-up. So it's really important to have timely follow-up, especially when you're running an astrophysics survey, because an astrophysics survey, it's not optimized for self follow-up. So you have to have dedicated true follow-up. And this is because when you have an arc of less than an hour long, especially for these close approaching asteroids, the sky plane uncertainty can grow fairly large. Just within hours, the positional uncertainty can go from tens of arc seconds to arc minute across to many degrees across. And so for Zwicky Transient Facility, what I would do is sometimes, I had permission, was to interrupt the flow of the survey to use the 7x7 degree field of view of the survey to do self follow-up. But that would be like a disruption, but it could be productive. But the majority of follow-up assets in the world are not going to be as large as Zwicky Transient Facility. So instead, we have to act more quickly. And this is a concern for the Rubin Observatory, because Rubin Observatory is following the same formula, and which is being optimized for astrophysics and not for the self follow-up of the kind of objects it's going to find. Rubin Observatory is going to be going to magnitude 24, so we'll detect lots of objects, but not very many people are going to be able to follow them up because they're going to be magnitude 24th or fainter. So they're going to have to devise a way to do self follow-up, or we're going to have to invent new methods for doing follow-up, in which we can overcome this problem of the sky plane uncertainty growing too large in order to localize them within a reasonable number of images. So we also do cometary follow-up, cometary, or let's say characterization. We do spectroscopy with the spectral distribution machine. So this is a spectrum of phaethon right here. Phaethon is a mixture of a very low albedo kind of object, almost like featureless spectrum. It has a fairly comparable spectrum to the solar spectrum. There's not very many features that can be identified. But this is a capability not just to do astrometric follow-up that we want to expand on. So we've actually been following up C2022 E3 with the SCDM. And I'm working with a student to try and measure the cometary gas production rate of the cyanogen gas and the carbon diatomic carbon, which are in the 4,000 to 5,000 angstrom range. So I will probably finish up here right now, but I'll like to mention, as I said before, is that we have to invent new methods for following up asteroids, which are fairly faint. So one promising method is something called synthetic tracking, in which you take many exposures and you co-add them together using the most probable trajectories for NEOs, or if you know before the fact what the rough trajectory is, you can actually automatically stack all the images, and that way you can reach a limiting magnitude that would be better than what you would have based on just a single or a few images taken separately. But that's all I'm going to talk about now. I wanted to talk a little bit more than just the background of the comet and the discovery, but also about the mechanics that the things that go behind the scene that help result and that help contribute to these discoveries.